So we've seen this formula before. So whenever you have a vector u, so this is your vector u here, it's 2 across and 5 up. Whenever you have your vector u and you project it on your vector v, this is our vector v here. If you project it onto here, then if you get this vector and project it onto v, then you're going to get this vector here. You're going to get this vector here. So in this video, we're going to investigate what happens when you project it. If you look at this, v is 3 across, 1 up. So the gradient is a third. What happens when you project u onto, let's say, 6 across, 2 up? So it's in the same direction. So rather than projecting it onto v, we're going to project it onto v where it's in the same direction. You can see it's 6 across and then 2 up. So here it should give us the same answer. It should give us this length here. When you project the vector v onto the vector u onto v, you're going to get this length. What happens when you project it onto v, where v is, let's say, 3 times as long, but in the same direction? So the gradient of so the gradient of v, the gradient of v here will be 1 over 3. What happens when you project it onto, let's say, a 2 over 6? Same gradient. Remember, gradient, we can think of gradient as being the direction. What happens when you project it onto 3 over 9? All these are in the same direction. But the thing is, when you project u onto 3v here, it should give us the same answer. When you project u onto 2v, it should give us the same answer. The answer should be this vector here. It should be this vector here. When you project this onto here, it should be this vector here. So in this video, we're going to see, we're going to illustrate this effect. So let's project v. Let's project u onto v. So this is our formula. We need to perform the dot product. No, we're going to need to perform the dot product. So it will be this times this plus this times this. That will then give us this. We need to work out the magnitude of v. Well, the magnitude of v would be this. The magnitude of v would be 3 squared, and then it's really us using Pythagoras, and then this squared, which will be 1. So the magnitude will be root 10. So looking at this, we need to get the dot product divided by this thing here. Remember, it would be this squared, which would be 10 because of this squared here. And then we need to times it with the vector v. The vector v is this one here, the vector v. So we need to times it with v. So that will then give us this. So now this times this, and then this times this. We will return back to this later on. So now let's look at a case where we double. Hang on. Now let's look at a case where we double the length of v. So we now need to look at this vector v here, where v is 6 across, and then 2 up. So now we need to look at the case where it's 2v. Okay, so 2v would be this. So now we need to work out 2v. So we are looking at a new v, which is twice as long and twice as high. So now do the dot product on this. This times this will be 12. This times this will be this. The magnitude will be root 40, but when you square it, it will be 40. And then the vector is this thing here. So that will then give you this, and then simplify this. That will then give you this. So later on we will need to do this times this, this times this. Now hang on. So let me summarize. So when you project u onto v, in the case of v being 3 across and 1 up, it gave us this. And then when you project it onto v, where this v here is 6, 2, then when you project u onto v onto this V here, it gave us this. So now if you look at this, if you so basically this length here is this one here, and then 2V here would be this thing here. But then if you look at this, our final answer for V would be this. Our final answer for this one here would be this. But then if you look at this and this, this is twice the size of this. But then you know you've got to get this times this and this times this, this times this, this times this. Well, this thing here is twice the size of this. But then if you look at this, this is half the size of this. So when you get this times this and this times this, they're exactly the same. They're exactly the same. So what I'm trying to illustrate here is that when you project U onto a unit vector, it doesn't matter if this thing here is 1, 0, or if it's 2, 0, or if it's 3, 0. It doesn't really matter. The magnitude of what you're projecting onto, it doesn't really matter. It only matters that it's the direction that matters, not the magnitude. So it doesn't matter if it's 7, 0. It will still be the same. I will continue in the next video. Okay.